What's the quantum?
Time allocated.
No. What's the quantum? No. The maximum time allocated to a process. Now, of course, you could have turned it around by the end, but that's the key word I was looking for. Okay, it's the maximum amount of time allocated to a process for the processor. Now I come back to you again. What's the advantage of a very long or disadvantage? Now let's check with advantages of a long quantum or disadvantage.
CPU-bound processes to finish.
Is that a good idea, to allow CPU-bound processes to finish without interruptions?
Well, it depends on the system. Many CPU-bound, IO-bound processes are not.
Yeah, but okay. So you think it's a good idea to have a long quantum? Okay. Now, what's the advantage of long quantums? I know they may not be the most perfect, but why should we go for a long quantum? What's the advantage of that? Any idea? Anybody? Say again? Yeah, it will lead to less context switching. So if you have long quantums, then we'll switch, less processes will be switched, and that will be more efficient. But of course, what's the disadvantage of long quantums? Yeah, the average turnaround time will be increased. Why would it increase the average turnaround time?
Each process would have to wait longer until it gets to use the CPU.
Yeah, but they're the same processes. If we had the shortest job first, they'll be flying. Because sometimes if we have the long job comes ahead of the queue, then it will delay every other process because it would not interrupt it. It will be like first in, first out policy. The job comes in, stays there until it decides it no longer needs the CPU. That's sometimes not a good idea in interactive systems. Right, okay, so maybe we should go for a shorter quantum. So what's the advantage or disadvantage of shorter quantum? If we have short quantums, that's a good idea?
You'll get more context switching.
Get more context switching, so that's less efficient. But what's the good point about it?
It's more efficient because all the processes are running.
Yeah. Is it more suited for interactive processes? Yeah, so shorter quantums would probably be more suited for interactive processes. It gives but it has the problem of context switching. What would be a good recommendation of length of time for a quantum? What's a nice time for a quantum? The length of a quantum that you'd recommend. If you are to set up, you're the administrator, system administrator, you need to decide how long the quantum is. What would be a nice length? 80% of what? Yeah, the number 80% rings a bell, but 80% of what? Okay, 80% of the CPU cycle of most of the jobs, or 80%, maybe 80% of the processes should work without interruption. You shouldn't be interrupting every process, especially the shorter cycle CPUs. Let them run to completion, only interrupt the long ones. So, any other recommendation? There's a couple of recommendations. Can't remember the other one. Right, okay, what else did we do about processor handling? Give me one condition where the CPU may be lost by a processor, may be taken away, voluntary or involuntary. If the quantum is exceeded, then it's interrupted in preemptive systems. Any other reason why you might lose the CPU? If a job is completed, normally or abnormal? Either, yeah, okay. Any other reason? If the program what? If the process requires input or output, then it will issue an interrupt, I/O interrupt. So I/O interrupt is another reason why we might, process might lose the CPU. If it commits an error, such as what? Give me an example of an error. Division by 0. Any other issues or problems or errors? If it access memory out of the bounds of the process or where it shouldn't be accessing. Okay. So if we are to select the next process to allocate the CPU to, give me a policy that you might decide to use. Shortest job first. Is this guaranteed to give good performance? Shortest job first or first in, first out? Which one is, you think, is the better performance? Shortest job first, right, okay. How would you measure the performance of these policies? How do you measure? How do you say this policy is better than that policy? Based on what? What would your measurement be? Average turnaround time. That would be something that... Average turnaround time. What is turnaround time? It's a time taken from submission of a request for execution to the end of execution. And what's a quantum? A quantum? A quantum? Okay. Right, okay. Today we'll talk about another topic. Anybody having any problem with any of the questions in the tutorials? Okay, today we'll talk about the topic of process management. But basically how to manage processes or applications running. We talked about the processor management in the past. So this is another manager, a different manager that has different priorities and different functions. And its main task is to make sure that these processes operate, to the best, the most efficient manner. So there are a number of topics we need to know or talk about. Something called spooling. And the race problem within processing. Then we also have process synchronization. And within process synchronization, we'll be talking about semaphores. And we'll also be talking about deadlocks. Which occur in processes or in a system, basically. So I mentioned a few of those here today. We'll talk about spooling and the race problem that keep happening. Synchronization problem we'll talk about next week. And we'll try and cover deadlocks between today and tomorrow. So just briefly, about spooling, and spooling stands for simultaneous printing operation, simultaneous printing operation online. And it's a method or a technique that was used to help reduce the effect of those slow devices, and in this case the printer, but similar idea can be used when dealing with hard disks or with other mechanical devices that can be lead to slowing down of the processor. So normally we know the processor would be running or executing instructions and processes, and one process time can be brought into or allocated the CPU. But as processes starts executing one process, as it sends its data for printing, usually it might require to do a bit of reading of data processing and sending some data to the printer. And it might have to wait for the printer to finish before going to the next one. And the printer may take a long time. Obviously, we know printer is extremely slow device compared with the CPU. So if it needs to wait for it, it's going to take a good bit of time. We know the printer is a dedicated device. That means it cannot be shared. You can't print 2 or 3 reports simultaneously on the same sheet of paper. So if another process, number 2, wants to print, the printer is busy, so it has to go into a wait. So they wait until this one finishes. And so the slow printer is not just going to delay that process, it will also delay all the processes that need to use the printer. So instead, to improve the performance, they've used spooling, and spooling usually involves a buffer. And the processes, instead of sending their output to the printer directly, but they don't know, but it's directed to some buffer in memory. So they're allocated certain space in memory. They think they're sending their output to the printer and they start printing, but because its main memory is so fast, data is put here, and they're told it's okay, it's got printed. So the process will go back and keep on processing and keeps on printing, while these ones as well, they think they are already printing as well. So they keep on printing. Each one of them thinks it has direct access to the printer. And whenever, say, process number 2, let's say, finishes, terminates, then we have a small process here that manages this operation. It will take its output and direct it to the printer and start printing. So it could be printing. This one is already finished while its output is being printed. And then maybe this process as well says, I'm finished. So it finished and it's gone. And we haven't even started actually printing its stuff onto the printer. But at least we got them to get moving. They don't have to wait for the printer, this slow printer device. So in effect, what we've done, we've turned this printer that's a dedicated device, that's mutually exclusive device, that's another term that's used a lot. Mutual exclusive device is a device that can only be used by one user at any given time. So we turn this dedicated, mutually exclusive device into a device that seems to be used simultaneously by other processes, even though in reality it is not. That's the technique. And hence the term virtual device. So we have mutually exclusive device, which is, there's also another name for it, that's a dedicated device. Or a shared device, the opposite, the extreme, or what's known as a virtual device. So a virtual device is a device that by its nature, it's a dedicated device, but we manage to make it appear as if it's a shareable device that can be used simultaneously, even if it still remains as a dedicated device. But all the processes, and within this system, it appears to be a shareable device. So that's spooling, and that's the terminologies of dedicated device and a mutually exclusive device and a shared device and a virtual device. So, just quickly again, what's a virtual device? Do you remember? Yeah, that we've managed to turn it into becoming a shareable device somehow. Right, another problem that we will talk about, well, that's basically spooling. The race problem, it seems to happen again in multi-programming environment where we have a number of processes executing. And generally, processes, they don't have access to each other's memory. Remember, we said if we have memory and we allocate some process somewhere, allocate it one continuous or non-continuous space in memory, that it's only allowed to access parts of memory within that range. So if there were two programs or two processes executing, they do not have access to other processes' memory. And in this case, they also don't have access to each other's variables. And there's very little, they cannot communicate together. So processes executing, when you run two programs in your machine, there's no way within the program that you can tell your program to go and access the variable on the other program or process. So that's not done. So there's no way for these two processes to communicate. They can only communicate at the moment in their present format through an external device or externally. So this one can read or write to a file on the hard disk, while this one can read from that file. That's one way of how we can make those processes communicate together, maybe. In the newer system that we'll talk about next week, where we have parallel processing, or we have the same process that maybe multiplies itself or copies itself onto the same area, but now suddenly we have two copies of the same process on the same memory area, or even more, we can have 3 or 4 copies of the same process, and they can run independently of one another. Each one of them can run as a separate process, and yet they are all executing from the same memory location, and they all have access to the same memory variables that the original process had. And that way they can communicate. But that's a different area. We'll talk about it later. But that's the proper form of how processes can actually communicate together and quicker. Otherwise, if we're running individual copy of each process in its separate memory area, then they cannot communicate within the memory area. They can only communicate through external means, and maybe reading or writing from a file. And that's how things used to be for a long time. But they also had a problem. So we need to synchronize between those, even though, we'll be talking about the synchronization in parallel processing, but even those here that are not really considered parallel processing, two separate processes accessing the same file, they could have issues and problems. And one of the problems they had was called the race problem. So the race problem, you can imagine that in a bank, for example, if you had your bank account in the bank and let's say you had 2,000 euros, and then there are two programs or processes that are executing, say, somebody has lodged some money into your account, so now it's being processed by a program and got to the point where it said, right, I'm going to add 1,000 euros to this balance, so hopefully you should have 3,000. While another process, and maybe the cashier, so maybe you are standing at the cashier and you've just handed in cash money to be lodged into your account, and the cashier is executing the process and located your record and said, right, I'm going to add 1,000 euro, and hopefully by the end of those two transactions your balance should be 4,000 euro. So let's just follow those two transactions. The way things work normally, in order to update this record in the database, normally you'd read that record and you say, send a request to get me that field. What value is it? What's the balance? I need the balance. So you get back balance equals 2,000. So what do we normally do? We add the 1,000 to it, so balance equals the old balance plus 1,000, which becomes 3,000, and then you send out there and you say, write the new balance of, this is 3,000. So this is going to be overwritten here, 3,000. So this is the normal way of operation. Similarly here, now if this guy wants to update your record, they'll follow the same procedure. Send a request, what is the balance? We get the response, balance is 3,000. Add to it 1,000, so it becomes 4,000, and write the now 4,000 there, and this is your balance. And that's the way things should work. Except the problem is sometimes that requests come in at the same time. So if this guy sends in order to write the €1,000, sends a request, while at the same time this guy is sending the request and the balance is 2,000, say, what's that balance? And we get the response back and we get told the balance is 2,000. This guy says, add 1,000 to it, it becomes 3,000. This guy said, add 1,000 to it, it becomes 3,000. And those two guys say, write the new balance. So whoever gets there first, let's say this guy got there first, so it'll be writing 3,000. But then, a moment later, this one arrives and says, overwrite that, it's 3,000, so it will overwrite this and becomes 3,000. You end up with a 3,000 instead of 4,000. So this problem can be solved by locking this record. Whenever there's a user that's using it that intends to modify it, well then, don't allow other users to take information from it if they intend to modify it as well. Lock it until this guy finishes. So hopefully if this guy sends a request, this guy sends a request first, lock it. So when this request comes in, it's locked. You hang on here for a few milliseconds until the record is updated or released. So hopefully when this one updates it first, then we send the new balance to that record. So it's called the race problem. So you need, we'll talk about locking those records again when we get down to synchronization as one of the means of solving those problems. So this comes under process kind of management, managing these processes. So what we'll talk about today is deadlocks. And with deadlocks, first we need to know what deadlocks are, how to identify that there is a deadlock, how to prevent deadlocks, how to avoid deadlocks, so all these things. So basically you need definition or explanation of deadlocks and identification, or how do you actually know, detection is a better word, detection of deadlocks, avoiding deadlocks, or prevention of deadlocks. So we'll talk about, first, what is a deadlock? Let's see how does it happen first, and then we'll be able to explain, maybe come up with a good definition of a deadlock. So generally, a deadlock occurs first in multi-programming environment. It never happens to one single process. It only happens to two or more processes that they might get deadlocked. And a deadlock leads to interruption of execution. So if the process just stopped working. And the problem with deadlocks is that processes on their own that are deadlocked, they'll never come out of that deadlock. They're stuck on it forever. Unless there is an outside intervention, that's it. They don't work anymore. They sleep. They go into a waiting state that they never come out of. So, and how does it happen? We have an example of, talked about this maybe in the past, where we have two users, and And we talked about the chef, the two people that want to cook some meal. And in order to cook the meal, they need these two tools, and the two tools cannot be shared. So there's a number of conditions that if they all got together, they could lead to a deadlock. So again, imagine if we have two persons, or two users, or two processes, and they're both chefs, and they both share an apartment, and they both want to go to the kitchen and cook something to eat. And they both will require some tool, maybe a frying pan, and maybe the kettle, or something, or, yeah. And, well, the kettle is maybe shared. So let's just say a knife or a fork, just a nice fork. A big fork that's used for stirring the food. Now, you need those two tools, and these two tools cannot be shared. No two people can use the same frying pan or the fork. And if they walk into the kitchen, and they both need those two specific tools in order to cook whatever they want to eat, each one of them. And if they walk into the kitchen, this guy reaches for the frying pan. No, let's say the handle is closer to this guy, so this guy reaches for it, so he has it. Now, the arrow, we have the arrow, if it's pointing from the tool or from the resource, I call this resource 1. Then if the arrow is pointing that way, that means this resource is allocated to this user. And this person here reaches for this fork and grabs it there. And this fork, or this resource number 2, is now allocated to this user. Now, this guy then tries to reach for the fork. So the arrow pointing this way is going for that fork. And we call that a request. There's a request now from person number 2 or process number 2 for this resource number 2. Resources are generally lined up in a square, so we'll use those symbols. But this tool is already gone. It's already been allocated to someone else. It's not available, so this guy has to wait. So this guy enters into a waiting state. Why? Waiting on this tool. He knows this guy, whoever has it, will finish soon with it and will release that tool or that resource, and that will be available, and then they'll go ahead and work. That's the way things work normally in a system, in any system. If you have a number of resources, you need one more resource. If it's not available, wait, and then it will be released by its user. In the meantime, this user here, this process, needs that tool, so they put in a request for it. They go and try and take it. It's not available. It's allocated to someone else. So they put a request, and obviously it's not available, so they go into a waiting state. So now we have these two processes waiting. They're both of them asleep. Each one of them is waiting on a resource, hoping that resource will soon be available. And in most systems, the resource will soon be available. Except in this system, it happens to be that they're waiting on each other for resources. So this guy is waiting on this resource that's allocated to this guy, that this guy has it, and he's going to sleep waiting, hanging on to it. He's not going to release that fork. And this process is waiting on another resource that's already allocated to this process that's already waiting, sitting asleep, hanging on to this resource and waiting on that resource. And as you can see, if we follow these arrows, they lead us back to the same starting point. And we call that a circular wait. So a number of conditions happen, if you notice, and they're important for us. First, these resources are not shareable. What do we call them? Mutually exclusive resources. That means if we could share the resources, there'd be no problem. There'd be no waiting at all. It's like this room. We're sharing this room. We're all in it together. If it was only one person can use it, then it would be an exclusive room. Then we couldn't use it. We'd be a long queue waiting outside the room. But in this tool here is exclusively only used by one person, by one user, and therefore the other user has to wait for it. The other point is that, as you can see, this one here is waiting. And while it's waiting, It's holding onto this resource. It's not releasing. If this guy who needs this resource, and if it found that this resource is not available and has to wait for it, if they had released this resource, the first resource, instead of holding on to it, there would be no deadlock. Because this guy would have then found that it's available and used it, finished and released both resources that can be used by this one. But in fact, this guy held on to this resource and went into a waiting state. Similarly, this guy that has this resource, when it couldn't find this resource, it went in a waiting state, holding this resource. So that's another little issue. Hold and wait. Some textbooks call it. Hold and wait. If we have a hold and wait, if it's allowed in our system to hold a resource, and then you need another resource that's not available, I'll go waiting, sleeping, while I'm still holding the initial resource, and that situation is called hold and wait. And that's one other condition or situation that gets us one step closer to a deadlock. So now, the fact that these resources are not shareable, and the fact that every user can hold a resource and go and sleep holding on to that resource, and now, if in our system we could say to this guy, you're waiting, you're sleeping, you have a resource, you're not using it at the moment. If we can take it away from that user and allocate it to another user, then we'd solve the problem. But we couldn't do it here. So this system, anybody has a good name for it? A system where you cannot take away resources from a user. A non-preemptive. We noticed that with the CPU in the processor manager. So this is a non-preemptive system. Could anybody remind me what a non-preemptive system is?
Can't be interrupted.
A process cannot be interrupted and a resource cannot be taken away from it until the process gives it up voluntarily. And what's a preemptive system? So if we are allowed to interrupt a process and take away a resource from it, then that's a preemptive system. If we have an unpreemptive system, as the case here, and if the devices or the resources are not shareable, and if we allow everyone to hold onto a resource and go in a waiting state, and if we ever get into this situation where we get into a circle, where this resource, if we follow the arrow, needs this user requests this resource that's allocated with this user, who requests this resource that's allocated to this user, we got to the same point. That's called a circular wait. So, and that's the final circular wait. That's the final straw. That will lead to a deadlock. So if we have those four conditions, and these are known as the four conditions that are required for a deadlock, not one of them, not two, not or, it's and. The first condition, and the second condition, and this condition, and this. If the four of them are available in a system with a logical and, that means the four of them have to be within the system. If the four of them are available in any system, then we're going to have a deadlock. And if we want to stop or make sure that we do not get a deadlock, all we have to do is very simple. Just eliminate one of these conditions from the system. If we can eliminate, if we can say, hey guys, all our resources are shareable, then we'll never have a problem. We'll never have a deadlock. If we can't solve that, then let's say you cannot hold a resource and go into a waiting state. So if you have one resource, you need another one. If the second one is not available, you need to go in a wait. You better release the first resource that you have. If we can do that, then we'll never have a deadlock. So those four conditions are absolutely, the four of them need to be available in the system in order to have a deadlock. And if we want to prevent a deadlock, if you want to design any system that will not have a deadlock, then make sure one of these 4 conditions does not get implemented in your system. And just so you'd know why do they happen anyway, deadlocks, is that as long as we have resources that are not shareable, and as long as there are not enough resources, there are more users than resources, then most likely we're going to have deadlocks. So especially if those 4 conditions, if they become available in a system, then they're going to have a deadlock. Now, so basically, now we have a good idea of what a deadlock is. A deadlock, some people call it's the deadly embrace. It's like this number of processes that kind of entangled together through requests and allocations of resources that leads them to go into a halting state, a waiting state, doing nothing. One is waiting on the other, and none of them ever gets out of this situation. So a deadlock, also notice that it doesn't happen with one single process. If one single process in a system, let's say we have 50 processes running, but there's only one of them that stayed there for hours, never finished. We call that starvation. We don't call it a deadlock. A deadlock must involve more than one process, at least 2 or more, and they must have this circular wait, that one is waiting on the other, one is waiting on the next, and comes back to the first one. And we call that circular wait. So that's a deadlock. So you can kind of make out the definition of deadlock by either how does it happen, what does it involve, and eventually, in a system, again, you could have 50 processes running and maybe 4 of them are deadlocked. It's very difficult to know because the other 46 processes are really busy working, printing, opening files, writing, and things are moving. It's just those 4 processes are deadlocked. So it's very difficult to detect a deadlock. Because there's no error. As you notice here, there's no error. There's no error messages. You don't get an error because a process needs a resource that's not available. That's normal. And it goes into a waiting. It requests, okay, give me an interrupt when it's ready. It goes sleep. We don't even allow a process to keep checking, is that resource ready? Is that resource ready? Is that resource ready? That wouldn't be efficient, would it? From what we learned last week, that's going to be a busy wait. You sit and wait and do nothing, but you're checking all the time, then you're consuming this CPU resource of checking. We don't want to do that. So most of the time, it's better, more efficient, to go to sleep based on an interrupt. So you'll end up having few processes that are asleep, waiting on certain resources. So it's not an error situation. You don't get notified there, here's an error. You have 4 or 5 processes sitting waiting. Your busy is real. Your system is busy working with the other 65 processes. And so we'll see how to actually do we detect a deadlock in a system. So what we know now is, let's look at how do we actually prevent a deadlock from a system. And any idea? How do we actually prevent a system from ever having a deadlock? Very simple. Make sure one of these 4 conditions is not in the system. So how could we make sure that the devices are shareable, are not mutually exclusive? Any idea? Right, that's what mutual exclusiveness is. If you keep locking things, then you're going to have, if I lock a resource and you need another resource and you lock that resource, then we'll end up in a deadlock. That's really one of the causes of deadlocks. So how could you say our devices now are not mutually exclusive? They're not dedicated devices. Is there an idea, yeah? Spooling is one idea that can turn these printers, that are dedicated devices, we turn them into shareable devices. So they are known as virtual devices. So if we can turn all our devices as virtual devices, all our non-shareable devices, those devices that cannot be shared, if we can turn them into virtual devices, then we'll never have deadlocks. So one example of removing this, eliminating this from our system, is by turning our systems into virtual devices. Virtual devices, and that one example is spooling. But spooling is used for printers specifically. But the similar idea, maybe, if we can apply to other devices, then that's it. We don't care about the rest. We know our system will never develop a deadlock. But it's not always easy. A lot of the times we cannot do that. Hold and wait. Can we stop that? Can we decide, hey guys, you can't hold a resource while waiting for another one. Sometimes I take a printer, I start printing, and then print half a page, and then I need to read more information from another file. I go to that file and it's busy. Someone else is using it, so I'm going to wait for it. So it's a good idea to release the printer and give it to another process that I've already printed half of my report page. Give it to another printer to start printing on the same page. May not be a good idea. So printers are really difficult. And there's so many other devices that are difficult to do that. But there's a way of doing it where a process never have to give up a resource. How about this? What about if we ask all processes to declare what resources do they need at the very start of their execution. Let's say your program says, I need 2 files and I need a printer. Another program says, I need a hard disk and something else. And if we can, before we allow a process to start executing, we say, hold on, I'll give you all the resources you need now. So you never have to be waiting or, you'll never be interrupted waiting on any of those resources. Here are your resources. You needed those 3 resources, take them. And you start executing. You'll never have to stop or wait. And when you finish, all your resources are going to be available. We'll allocate them maybe to other resources that need them. That's another way of doing it. So in such way, you'll never have to sit and wait, whether holding a resource or not holding a resource, because you have all the resources you need. So that's by declaring in advance all resources, allocate all resources required to a process. Isn't that a good idea? Probably is. Anybody can see any problem with that idea? It will eliminate, for certain, deadlocks. There'll be no more deadlocks. Anybody can see any issue with it?
One process has all the resources allocated to it, then like other processes, it's not efficient because other processes won't be able to use that, even though a process isn't using all the resources at the same time, they'll still be held.
Okay, yeah, that's a very good idea, a very good point. Yeah, but no process would be waiting on them because we don't allow any process to start running unless we give it all the resources it needs. If the resources are being used by someone else, they'll have to wait. They can't start executing until their resources are available. Once we allocate all the resources to any process, then it will run to completion. But the problem, yes, as you said, it's efficiency. Sometimes you might run, for example, a process for 10 minutes, let's say, very, very long process. And it only needs to print 1 word at the end, to a printer or a file in a hard disk. So given it that printer for the first 10 minutes that it doesn't need it, that's a lot of wasted time of the resource that we could have allocated to another process that needs it. So yes, it'll be inefficient use, very, very inefficient way of utilizing the resources that you have. So if you only need a resource for 1/1000th of a second, but we give it to you for 2 minutes, that's way too much. Instead of just giving you the resource, use it and release it. Okay, maybe you can ask, release the resource as soon as you finish with it, but that's fine if you need it at the start of your execution. But if your process doesn't need that resource until near the end of its execution, there'll be a lot of inefficient time. But it can be done. So that's at least one way of doing it. If we decide, okay, it's not efficiency, we don't want deadlocks. It has a high cost, but we can get rid of deadlocks. What about circular wait? Circular wait is actually, that's when a deadlock happens, when you end up having a circular wait. So can we prevent a deadlock? Can we prevent circular wait in a system?
You block a request when that resource is being used. There is a process to block the request.
Once you start going into blocking, it's probably more likely you're going to have, a deadlock than not. Well, that's how a deadlock happens, by blocking another process from taking that resource. There's another technique, or there's another idea, is that if we make a list of all the resources we have in our system, put a hierarchy kind of order onto it. So let's say we have the frying pan, resource 1, and we have resource 2, whatever. Let's say there's a hard disk here, there's printers here, and so on. So if we put our resources in a list and we say, listen, if you need any resources out of our resources, this is the way to order them. You order first the resources that are on top of our list, and then go down to the bottom of the list. Don't order them randomly. Imagine now in this example, we have two processes, two users came in, and they both need resource 1 and resource 2. Here is the resource 1 and resource 2. The problem that we had that had led, to our deadlock is that these two processes that came in, they went in, one went for resource 1, one went for resource 2. Immediately as they came in, this one went for resource 1, this one went for resource 2. Now, this process needs this resource and that process needs that resource. No. If we had said, any process that come in, only first go for resource 1. You're not allowed to reach for resource 2. First, if you need those two resources, you have to go for this one first and then this one. So the two processes, they'll be competing for the same resource. The one that gets resource 1 first can carry on. The other one will come in, says resource 1 is already allocated, has to wait. So now, if you have resource 1, you can take your time, you can go to resource 2, it's going to be there. So by putting an order in the resources you request, you're going to remove this thing of different processes going to different resources. If we have all our resources in some order, that it's going to lead processes maybe to compete for the first available resource, but once the first one that gets it can carry on to the next resources while the other one has to stop. It cannot reach for the other resource. And that will lead to the elimination of circular wait. Yeah, basically, we block it from taking resource number 2, but with some structured kind of, is this similar to what you were suggesting? Yeah, okay. Maybe I misunderstood you, but if we can make them maybe go for that one, but not this one, block them from getting another resource maybe. But we're not blocking them here. We just tell them, listen, you have to go for that one first, and then this one, and this one. If you don't need that one, you can go for the other one. But at least this should prevent that. You might still have processes waiting, but not in a circular wait. That will solve the circular wait issue. So that is the prevention of deadlock. So you might be asked, how would you prevent a deadlock? And the simple answer is by eliminating one of those 4 conditions. Of those 4 conditions, for a deadlock to happen, the 4 of them be available in the system. If we can eliminate one of those 4 conditions, then we'll never have a deadlock. But then might be asked to have some suggestions of how any of those conditions. The non-preemptiveness is a bit difficult one. You know, if you allow preemptiveness to interrupt a process while it's executing, it's also a problem. So maybe it's better to allocate all the resources in advance as well that could solve this issue. But you need to be able to give some kind of explanation of how to eliminate either of those processes. First, you need to be able to explain what each of those conditions actually means. Like, what do we mean by non-preemptiveness? That's in a system we cannot interrupt a process and take away a resource from allocated to that process until it finishes with it. Hold and wait, you need to understand what it actually means. They might have different terminologies in different textbooks, but these are, you know, the names might slightly be different, but these are the actual 4 conditions required for a deadlock. Now, avoiding a deadlock. We need to talk about how to avoid a deadlock. Because we can't always prevent a deadlock. It's not always possible to say, hey, in our system we're going to prevent deadlock altogether. It may not be possible. It's very difficult to actually remove one of these conditions completely from a system. A lot of the times it's not possible. So, in other words, there are many other ways where in other systems what they decided to do is they decided, right, deadlock is possibly, it may happen occasionally, so what we can do is avoid it for as long as we can. And if it does happen, we'll deal with it occasionally, but we try to limit the number of times it happens. So, we'll talk about now how to actually avoid it. And avoiding it is through an algorithm or a system that was suggested by one of the computer science people back in the 70s, where they decided they saw similarities and they saw that problems are starting to happen or deadlocks starting to appearing. And it's basically, they've started understanding that the problem is based on using resources, and there we have too many users and not enough resources. And they looked at other organizations, and maybe back in the 70s in Holland, banks operated very well, so somebody decided to see or study how the banks operated their loans and how they managed the money and try to implement it here. Looking at the money as being resources and people coming looking for loans. So let's look at how a bank did it. Well, we can't say they were always successful and they did good results, but at the time they thought banks really operated very efficiently. So the way they looked at a bank is they found this is the way banks operate. So we just have a quick example. Let's say we have a bank has whatever, total 10 million units of money or euros or pounds or whatever it is. And we have a number of users. So here's process number 1 or person number 1, person 2, person 3, and so on. They need loans. They need to take some loans. And the loans they need to take, let's say this guy needs 4,000 and this guy needs, 8,000, this guy needs 11, or maybe 11 is too much, 6,000. And they don't need to take them all in one go. They all apply to develop projects that hopefully maybe build factories or a shop or something, so they need a bit of money. They could be 10 million, right? So that's asking for 4 million. So this guy might need to build something, and they might buy machinery, and then train some people, and then start the production. Only when they finish and they start selling their material, then they'll pay us back. Otherwise, we'll have to give them money. But we won't give it to them all in one go, just in case the money disappears without project. So let's say this guy came in and asked for 2 million out of this. So that's what's the total request, total resource needed. And this is what's already given to the individual. And this is what's remaining to give or to be taken. So this guy requires 4 million, taken already 2 million, so 2 million is left. Let's say this guy here, 8, already collected 3, and 5 is left. This one is, 3, and 3 is left. So that's the situation, let's say, of the bank at the moment. Total allocated, total given to the bank at this stage, this is what we've given out of the bank, so 8. So what's remaining in the bank, cash or safe, is 2. That's what we have left, 2 million. Let's say this bank here, this user here, user number 2 comes up and says, you still owe me 5 million in order to finish my project. I need 2 more million. Can I have the 2 million? This is the way the banks would look at it. The bank might look and say, 2 million. Right now, maybe I'm safe enough. I'm in a safe state at the moment. Let me see what safe state is. But the request comes in, the request, user number 2 needs 2 million. That's the request. Will we satisfy that request or not? Before they give the okay, they check. If we do, remember, if we satisfy this request and allocate this person the other 2 million they're looking for, will our bank still remain in a safe, secure manner or not, or state? If it does, then we'll approve it and we go ahead and give. And if our bank turns into an unsafe state, then we will refuse, we will not give. So supposing we did give this individual, so I'm just going to write here, originally the values are 3 and 5. So if we give this guy another 2 million, so this would be reduced to 3, and then we would have given them 5 in total. So because they'd have asked for 8 altogether, they've given them 5, remaining 3. Now, is our bank here in a safe way or not? A safe bank or a safe state is a state, or hold on, and we'll also would have given the 10 million out of here, and we have no more money in the bank. And nobody's going to bring any money in, because nobody has taken all the money that they've asked for. None of these factories is actually producing now. They're still consuming money. So in this case, we'll say, can our bank actually provide? How do you check if the bank is in a safe state? Can we give each one of those here the remaining money? Can we provide all the required money for every customer in our bank? We normally would pick the one with the least. This guy only needs 2. Will we be able, if tomorrow morning they all arrive and they say we need money, will we be able to satisfy them? So in this case here, we can't satisfy anybody. Because that guy with the least amount of money that needs it, we can't even pay them. It would have been great if our bank had maybe 12 millions and we still have 2 more. That would have been a good condition. But in this case here, no, our bank will not be able to satisfy any of our customers. So it's going to turn into an unsafe state. So let's go back to the way we were. Let's say this guy comes up and says, I need the 2 million. Will we allocate the 2 million or not? So not person number 2 now. Person number 1 comes in and says, I need the 2 million. We'll say, all right, suppose we gave them the 2 million. So the total given to this person is 4, and they no longer need money, and we would have given all our 10 million, and we have nothing left in the bank. Is this a safe state for the bank or not? By looking at this, supposing tomorrow they all come back. Of course, the moment you say, we give this guy, so this guy has taken all the money that they've asked for. Now, hopefully, their factory or their project, then we'll start producing money. And they'll bring us back the 4 million. So they'll pay back 4 million. That 4 million, we can use it to pay this guy here. So we'll give this guy the 3 million that it needs, and we'll have 1 million to spare. When this guy has all the 3 millions that it needs, then he'll pay us back 6 million. So we'll have, out of that 6 million, we'll be able to pay this 5 million, and our bank is still in a safe state. And therefore, in this request, we'll approve that request. Okay, so each state, the bank should be in a safe state, and with every request, they say, let's check if we did approve this request or satisfy this request, will it leave our bank in a safe or an unsafe state? If theoretically proved that it will leave our bank in a safe state, we'll okay the request. Otherwise, we'll refuse that request. So this is the basic idea of what became to be known banker's algorithm. So banker's algorithm is an algorithm used to avoid deadlocks. It does not prevent deadlocks altogether, but it keeps the system in an ongoing state. It's better than preventing deadlocks altogether, because with prevention of deadlocks, normally the cost is very, very high, because you might have to give a process all the resources it needs, that it only needs them for a very short time, very inefficient way of solving the problem. But with banker's algorithm, you kind of avoid deadlocks as much as you can, even though it has its own little issues, but that's the way it operated. Also, some of the problems that banker's algorithm has, that it only deals with a given set of, say, processes and given set of resources available. If another process comes into the system, you'll have to redo the calculation altogether. It doesn't always, it's not a dynamic way. It doesn't modify itself very easily. And there's a lot of calculation in it. So it has a bit of it's not the most efficient way. It also always assumes the worst scenario. It always assumes tomorrow these guys are going to come up and ask for their maximum resources. We need always to be safe and secure, just in case this customer or this process comes and says, I need the 5 hard disks now. It may not happen, but we always need to be ready for that event. And therefore, it looks at the worst event and takes care of the worst case scenario. And the worst case scenario tends to be always more expensive than in the reality. But that's banker's algorithm. Any questions so far? Good. I'll ask the questions. Name one of the conditions, one of the 4 conditions required for a deadlock.
Hold and fasten.
Hold and release. No, it's hold and wait. Hold and wait condition. Any other condition?
Mutual exclusion.
Mutual exclusion or, non-shareable devices. Okay.
Non-preemptive system.
Non-preemptiveness, yeah? A circular weight. Very good. What is non-preemptive system? Just describe or explain this condition, non-preemptive.
Systems would be like they don't waiting. There will be no interruption because systems goes on without any interruption in the past.
Okay, non-preemptive is we are not allowed. The system is not allowed to interrupt a process and take away a resource from a process. Is that what you said? Yeah. Right. How do you describe circular weight?
When two processes are,
Or more?
2 or more processes have requested resources, 2 or more
Okay. Anybody can put it in words? Just the circular weight. One is waiting on the other. If a process needs a resource and gets allocated that resource, right? No, if a process requests a resource, but that resource is allocated to another process that's holding that resource, but needs requesting another resource. But that resource is allocated to another process. If you reach the same point, that's your secular weight. Okay, so it's allocation. It's a circle of requests and allocations of resources. And if it leads to the same process, back to the same process, back to the same resource, then that's known as circular weight. And what's spooling? Yeah?
For the printing devices, it's a dedicated device that gives the impression that it's a shared device.
Say again?
Spooling is when you have a printer that is a dedicated device, but it gives the appearance that it's a shared.
Yeah. So printers that are normally dedicated devices, spooling makes them appear to be shareable devices. And what's the benefit of spooling? What advantages does it have?
Frees up resources because the process that was looking for the printer thinks the process is actually printing.
Okay. With the fact that it thinks it's printing, is that an advantage? What's the advantage in it? What benefit do we get into the system? Okay, it improves overall performance of the system, and specifically which part of the system that will actually improve? Yeah, it's the CPU doesn't get to wait as much because for the low kind of performance devices like a printer. So it actually improves the performance of the CPU by speeding, making sure, or it gives it the appearance that we have a very fast printer. Okay, and what's an average? What's a turnaround time?
It's the time from when the process is allocated to the time it's completed.
Yeah, from the time it's kind of requested for execution, from submission time to termination time. Okay. Condition. What's a banker's algorithm used for? No, is it? Okay. No, what's the purpose? What's the purpose? To avoid deadlocks. And how do we prevent a deadlock?
Removing one of the four necessary conditions.
Yeah, and how do we avoid deadlocks? Through the use of banker's algorithm. Who can kind of summarize banker's algorithm for me in a couple of statements? Anybody? Think about it just for a sec and see if you can put it in a couple of banker's algorithm. If you're asked to explain banker's algorithm, how would you describe it? Who wants to have a go?
The system always has to be in a safe position,
Safe state.
The safe state being there is always enough resources available if those resources are going to be requested, and the basic resources might be requested.
Okay, yeah, close. Anybody else want to have another go? How would you describe banker's algorithm?
Assesses the resources that are available or that are requested and what it has available, and then determines how much it can allocate while remaining in the safe state.
Okay, so it's a combination, but the main idea, what's the main idea in banker's algorithm? If a request comes in, what does the system or the bank manager should do or does, or how does our computer administrator or operating system implementing bankers' arrangement. If a request comes in general, what does it look for?
Checks to make sure that.
Okay. Yeah, go on.
Checks to make sure that there's always minimal resources available for whatever potential request there might be.
Okay, that's the one way of putting it. In a more general method?
Ensures first of all, it ensures the resources that is available with the bank. Suppose the fund banking for the bank manager, first of all, ensures that if the resources he can provide to the person who is going to take the loan. And suppose he's asking for 4 million.
No numbers. Okay, just keep it general. Yeah, I got the point. Okay, so basically the main idea is if a request comes in, is to check if this request is satisfied. Will it turn the bank into an unsafe state? If it will, then refuse it. If it keeps the bank after satisfying this request, if the bank is still in a safe state, well then approve the request. This is the general idea, and we can build around it. But usually you have limited number of resources. Some of them are already gone, some are still in request, and some will come back, but they'll only come back if the full resources are taken and finished. So the idea, if a request comes in, check. Satisfying this request, will it turn the system into an unsafe system or a safe system? If it's unsafe, well then refuse it. If it is a safe system, well then approve. And we have examples. You can look at the examples in the notes. Any questions? No questions. So who could tell me what is a deadlock? Now, the definition of a deadlock. What's a deadlock? Yeah. Maybe part of a definition we'll get.
Two or more processes are requesting resources in a circular.
Okay, very good. Two or more processes, that's very important. It's not one single process. Two or more processes that may be entangled in a waiting state, and an endless loop in an endless wait. So that kind of describes it. And then we say, what would cause it or what's required for a deadlock? And then these are the 4 conditions that are absolutely required for a deadlock to happen. Then how do we actually get out of a deadlock? So how do we actually recover from a deadlock? So it's something we'll talk about tomorrow. But generally, there is no easy way to get out of a deadlock. There's no kind of solution. You either prevent a deadlock from happening or else we're going to have a deadlock. And if we do have a deadlock, we need to terminate one or more of the processes. In some systems, probably happened to you many times before, where your computer just jammed, closed, stopped. And it's probably a deadlock. All the processes are not running, you get no response. And probably you've reached for the power button and switched it off, which is probably the worst thing, the worst solution that you could have had for a deadlock. But for deadlocks, yeah, we can terminate every process in the system, shut down the system and start again. There'll be no deadlock. But we can also select a few processes that are deadlocked. Let's go for them if we can identify them and delete them. And the rest of the process will continue. But that's also a very costly thing. You could end up deleting a process that's been running for 5 or 10 minutes, has done a lot of work, hasn't finished. And then if you run it again later, you'll probably have to do the same work. Sometimes if it repeats the same work, it gives you wrong results altogether. Like maybe adding a few totals, and then if you have to add again, they're already saved, and you could end up having completely wrong results. But then another way of doing, then the less damaging one is just out of these processes, select one of them which to terminate. And when we say terminate, that hopefully once you terminate it, it will release those resources that can be used by another process in the deadlock that then finish and releases its own resources, and then so you could end up removing or getting rid of the deadlock. And so that's really possibly the best way, is to select one victim process. And the problem or the dilemma becomes, which one is the victim process that needs to be terminated? And that's selecting the proper one. So we'll talk about termination tomorrow. But also something else we need to talk about tomorrow, that's detection of deadlocks. How do we actually detect a deadlock in a system? And I just need to know, what time are we finishing at? Are we nearly? Okay. No, I think we'll leave that till tomorrow. Okay, thank you guys. Did I give you the attendance sheet? Thank you. Okay, this is when we're supposed to stop, right?